Welcome to part 3 of Statistical Reasoning. In today's session we're going to start with the 8 big ideas in statistical reasoning. Let's not wait, let's go straight for it. The 8 big ideas of statistics. The first very big idea is data. The need for data. Statistics lives in data. Data lives in statistics. Data lives around statistics. Statistics lives around data. How data represent characteristics or values in the real world. So the need for data and how that data represent characteristics and values in the real world. How data is obtained. Different types of data, such as numbers, words, and so forth. Without data, statistics won't exist. Statistics is the science of interpreting and working with data. The second big idea in statistics is distributions. How is this data distributed? Is it distributed in a huge cloud? Is it distributed with peaks? Are those peaks the same? Is it distributed with a peak in the left and a plateau on the right? What does the distribution say to me about the data that I'm looking at? Okay, so distribution is a representation of quantitative data that can be examined and described in terms of its shape, its center, its spread, as well as unique features, folks. This is big, such as gaps, as clustering, any outliers that may be there, and so on. So first of all, big idea data. Then how's that data distributed? The distribution in a data set tells us a lot about the phenomena under investigation. We express the distribution or consider it by looking at its shape, center, and its spread, and the unique features like gaps, clustering, and also outliers. Now, outliers is a very sensitive point in my life. One does not just claim something to be an outlier because it lies way over there. You have to have the statistical backup that yes, in this distribution, the way the rest of the data is distributed, that is definitely an outlier. And there's processes and ways to do that. The third big idea is the trend in the data. Trend. Okay? A signal or pattern that we're interested in. It could be a mean for one group, the difference of means for comparing two groups, straight line or bivariate data, or a pattern over time for a time series data. So what is the trend in the data? We are looking at, let's say, female drivers and the cars they prefer, okay? Or the speed at which they are caught when they break the law of traveling at 60 kilometers per hour. There will be a trend in that data. The trend shows clustering. The trend can show a linear trend that are closely clustered together. Okay? If we just look at a dot plot, what is the trend shown in the dot plot? Workers in a factory and their salaries that they earn. Okay? What does the dot plot reveal about that? So what is the trend in the data? 60% of people earn less than 4,500 a week, or whatever the case might be. So there will be clustering there. And then here at the top, 5% people earn like 12,500 per week. So what does the data say? What is the trend in the data? So that I can make inferences and then go and do the search to see Was my expectations, are they justified? Then variability, the fourth big idea in statistics. The variation or noise around a signal for a data set. Variation or noise, such as measurement errors. Variability may also be of interest in that it helps describe and explain a data set, reflecting natural variation in measurements, such as head sizes of adult men. Okay, variability, big idea. The variation or noise around a signal for a data set. Okay, variability in your data. Very, very important. Okay, so models. Let's go back to variability for a second. You can do an experiment, for instance, on matric boys and their shoe sizes. Okay? So you can only measure their feet in centimeters, or let's say millimeters, and you will find different lengths. Now, what causes that variability in the data? Is the boy tall? Is the boy short? So you might want to bring in a second variable to look at. Why is there such variability in that set of data items if you just looked at the sizes of their feet? Okay, the next big idea is the idea of models. Okay? An ideal that's sometimes useful in understanding, explaining, or making predictions from data. A model is useful if it fits the data well. Now, in bivariate analysis, the model is a linear model, for instance, the one that we use in regression analysis. But that's not the only model that exists. If there's a trend in the data that's exponential, we will look at an exponential model to represent the data. Sometimes use of some examples of models that are the normal curve, straight line, a binomial random variable with probability of 0.5. Okay, so it all depends on what the trend in the data shows and how that can translate into a model. Okay, so again, I had a statistical analysis package that had over 250 models that were out there that could be fitted to the data. So all I had to do was put the data into the program and then run the analysis. And then it will come out with a model that best represents the data. Then another big idea is association. A particular kind of relationship between two variables. Information in one variable helps us understand, explain, or predict values of the other variable. Okay, so we see how the one variable behaves, and it helps us understand the second variable. An example, again, the shoe sizes of boys. The shoe sizes vary for the matric boys from, let's say, 7.5 to 13. Why is there such a big variation? So we bring in the second variable, the height of the boy. Okay, and sometimes there might be outliers. I had short friends whose feet were as big as mine. So that could possibly be an outlier. I mean, I'm 6'4". Okay, so the association may be observed between a quantitative or categorical variables. Now, remember, quantitative measures quantities, or categorical measures male, female, two categories. This also includes being able to distinguish correlation from causality. Okay? And it's not you get correlation, you distinguish correlation from causality through association. This is a big thing in statistical reasoning, the idea of causality. The one variable does not always cause the other variable to behave in a specific way. Even though the correlation could be 1, could be a very high correlation, it still does not explain causality. So association is what connects causality and correlation, and your ability to distinguish between the two. Does a high correlation tell us something about the causality in the relationship between the two variables? Again, samples and sampling, the 7th big idea in statistics. A sample, if you want to make generalizations about a population under investigation, you need to make sure that your sample, your sampling method and your sample size is chosen in such a way that you can validate your claims about the population. So the process of taking samples and comparing samples to a larger group, that is what samples and sampling is all about. The sampling process is important in obtaining a representative sample. Very important. Samples are also used to generate theory, such as simulating sampling distributions to illustrate the central limit theorem. Now that's something you're going to learn about when you go into a tertiary institution to study your statistics further. So, samples generate theory. Because they generate theory, the samples, the process of sampling and the samples themselves have to be representative. If you want to measure the most popular car driven by university students, you can't go and sit at the gate for an hour in the morning and look at the cars that come through the gate. Okay, you have to. That won't be representative of the population. It could be, but in many cases it won't be, because not all students have classes in the beginning of the day. So you'll have to sit there for maybe 2 or 3 days and tick off, and then you can generalize from that. And then lastly, the 8th big idea is inference. Ways of estimating and drawing conclusions about larger groups based on samples. Okay, so what are the conclusions you can draw from the samples, from the population or the sample that you investigated? This includes being able to differentiate between practical and statistical significance, as well as knowing the difference between finding no effect versus finding no significant effect. Okay, so that concludes our discussion of the 8 big ideas of statistics. Technology is also a very, very interesting discussion point in developing statistical reasoning. How can technology help? Well, Benzi in 2000 described how technological tools may be used to help students actively construct knowledge by doing and seeing statistics through the technological tool, as well as to give students the opportunities to reflect on observed phenomena. Technology does that efficiently and very quickly and very, very accurately. So technology plays a big part in the statistics classroom. He views computers, Benzi, as cognitive tools that help transcend the limitations of the human mind. So what you could have imagined by just looking at the data and organizing ordering the data. Could be something that you didn't see. Was there clustering? Was there an outlier? How was it spread? It's one click on a technological tool and you have that information at your fingertips. So technology is thus not just an amplifier of students' statistical power, but rather a reorganizer of students' physical and mental work. Let's look at commercial statistics packages that can be used in the statistics classroom. One of them is Excel. For analyzing the data and constructing visual representations of data and spreadsheets, you can use Excel or data analysis programs like StatGraphics that offer a variety of simultaneous representations that are easily manipulated and modified, as well as a simulation of different distributions. So those three important things. If you want to have a simultaneous representation, an easily manipulated and modified representation of data, as well as a simulation of different distributions, then Excel and StatGraphics are the programs that does that for you effectively and quite quickly. They are commercials, what we call commercial statistical packages. Then we also get the educational data analysis tools like Fathom. Now I like Fathom quite a lot. There's things that I can do in Fathom that I cannot do in Excel. So Fathom, these tools are intended to help students develop an understanding of data and data exploration. They support an in-depth inquiry in statistics and data analysis through powerful statistical and plotting capabilities, more powerful than your commercial statistics packages. And these packages give the user greater overall control in structuring and representing the data. Fathom also allows plotting functions, creating animated solutions, and has a dragging facility that dynamically updates data representations. For instance, in Fathom, you can go into your data set and you can delete once you've done a bivariate analysis and you've got your regression equation there with a correlation, you can remove the outlier and see immediately how it changes the gradient and the correlation, gradient of the line and the correlation coefficients. This helps reveal the invariant phenomena and the relationships amongst representations. Fathom is very good to do that, to see what changes and what doesn't change if I work with data. Then there's also the web-based and computer-based applets. There are a lot of applets that are there online that can help you work with technology in the statistical classroom. Okay? So these applets were developed to demonstrate and visualize statistical concepts. Applets are typically small, web-based computer programs that visually illustrate a statistical concept by letting a user manipulate and change various parameters. The mini tools, a particular type of applet, were designed to support an explicit learning trajectory to develop an understanding of a particular graph and its link to the data on which it is based. So what they're saying here is there are web applets available, and mini tools is one of them. The fact that they mention it means have a visit and see how you can use that tool. They wouldn't have mentioned this if the tool wasn't worth talking about. Then you get standalone simulation software, such as Sampling Sim is a program which was developed to provide a simulation of sampling distributions with many capabilities, allowing students to see the connection between individual samples, the distribution of sample means, confidence intervals, and p-values. Okay, folks, so there's your technology. The technology is available. Take it into the classroom. It, as they said, it develops the student's ability to see and do statistics. The last three tools on this list, Fathom, Mini tools, and sampling, were designed based on ideas about what students need to see and do in order to develop, very important, a conceptual understanding of abstract statistical concepts, as well as develop the kinds of attitudes and reasoning required for analyzing data. This is what we want learners and students to understand. Conceptual understanding of statistics. What does the concept do? What it doesn't do for you? And those three programs are designed to help with that. Okay, so Bucker in 2002 talks about two types of technologies. The root type software and the landscape type software. Very important. What is a root type software? Well, those are small applets and applications, such as the mini tools that fit in a particular learning trajectory. The landscape type software, you can imagine, is more broadly applicable. Larger applications such as Fathom and Tinkerplots, that's a new one, that provide an open landscape in which teachers and students may freely explore the data. That is not in mini tools, that is in Fathom and the other tools that we mentioned in our discussion. So folks, look at, you can pay, if you buy Fathom, you pay a student license for Fathom, I think it's 62 Rand a year, or you can buy the program. I'm sure you can buy a lifetime subscription to Fathom, just investigate that. But it's well worth buying the program and working with it. Okay, so the challenge of teaching statistics. You would have heard many teachers say, oh, it's so difficult to get this into the students' heads. Okay, why is that the case? Well, many statistical ideas and rules are complex, difficult, and counterintuitive. It is difficult to motivate students to engage in the hard work of learning statistics. Previously, we saw that there's a statistical anxiety. I was a person with a huge statistical anxiety. When I learned that I had to do statistics in my postgraduate, I was very afraid, and I made time to do every example in the book, every homework exercise that I could lay my hands on, only to discover, is that what this is all about? Okay, so that anxiety soon went away. Many students have difficulty with the underlying mathematics, such as fractions, decimals, algebraic formulas, and that interferes with learning the related statistical content. Okay, so if your mathematics, your basic mathematics, like multiplication, division, fraction, decimals, are not in place, then you're going to make and you're going to fall into little traps. And you're going to think it's the statistics that's difficult. In the meanwhile, it's the underlying mathematics. The content in many statistical programs may mislead students, causing them to rely on their experience and often faulty intuitions to produce an answer, rather than select an appropriate statistical procedure. Appropriate being the key word. Students equate statistics with mathematics and expect the focus to be on numbers, and it's not. On computations, on formulas, on the right answer. They are uncomfortable with the messiness of working with data. It's messy. It's a grey area. It's open to interpretation. The different possible interpretations based on different assumptions, and the extensive use of writing and communication skills in statistics. That is what makes it challenging, folks. There is no right. There's definitely a wrong answer if it's not appropriate. But in many cases, you will see that if you look at memorandums that are supplied about school statistics, there's always a range of answers that's acceptable. Okay, so if you are asked specifically to interpret something, people interpret things differently as long as that interpretation is statistically grounded and visible in the data and appropriate, obviously. And that is the open-endedness. That is what children have problems with, what teachers have problems with as well when they teach statistics. These are the most important goals for students enrolled in statistics courses, and that these goals are not concurrently achieved. Okay, the ones over here. There is a dissatisfaction with students' ability to think and reason statistically, right from school level up to tertiary level. The reasoning ability of people using statistics is really not as good as what possibly an algebraic reasoning or a geometric reasoning ability is. And it's because of that grey area that statistics creates. Statistics muddies the waters. And you have to look past the noise, past the variation in the data, to really see what's happening. And that takes development of that particular skill with learners so that they can reason statistically, at least. Okay, so the challenge of teaching statistics, the recommendations that are out there for us. And Cobb and McLean said this: incorporate more data and concepts when you teach statistics. Often when you open a textbook, you see there's 50 data points that are arranged already, that are ordered. And then there's the question, sketch the appropriate box and whisker plot. Where's quartile 2? Where does 50% of the data lie? Etc., etc. Okay, so those are neatly packaged data that suits that particular question, because there's a memo for that question, and the memo is more or less accurate with one or two answers with a small range. What these people are saying is, no, don't take data that is as clean as that. Take more data and concepts into the classroom and work with them. Rely heavily on real, not merely realistic data. So real data. Look at the election results in South Africa. Look at how they've differed through the years. See how the support of one party grew over the other. And try and find reasons, that type of thing. That's real data. And that's a huge data pool to work with. And then make inferences or conclusions based on the data, and obviously applying appropriate statistical methods to it. But real data, not nice data that is going to tell the story you want it to tell. Muddy the waters. That creates or develops the critical eye in the learner when you talk about statistics and statistical reasoning. There it says, focus on developing statistical literacy, reasoning and thinking through using more real data. As a teacher, that is our purpose, is to develop the literacy, the reasoning and the thinking, critical thinking skills in our learners in the statistics classroom. Whenever possible, automate computations and graphics by relying on technological tools. If it's possible, do it. use it, use the online tools, use the software packages to illustrate what the data is saying and what you see in the data, and then also to check, is it indeed the case? What I'm seeing, is that really in the data, or is my eye fooling me? Are my eyes fooling me? Foster active learning through various alternatives to lecturing. Collaborative learning, folks. The best way, I won't say it's the best way, but it is, that's a huge claim, but I believe it's a very, very good way to develop the critical eye and the critical ear of the learners in the class, listening to each other's arguments, pulling each other's arguments apart and saying, but now hang on, where did you see that? Prove it to me, I don't see it. That's a learning process, that's collaborative learning. Instead of you standing in front of the class, drawing pictures on the board and saying, this is this is that, this is how you get there. So encourage a broader range of attitudes, including appreciation of the power of statistical processes, of chance, of randomness, of investigative rigor, and a propensity to become a critical evaluator of statistical claims. For that purpose, you can use statistics or abuse statistics. Show how people use statistics to make claims that we know are not valid. We call that abusing statistics. And politicians are quite good at doing that as well. And people that have high reports that, let's say, for what was this big scandal in South Africa where they over-reported their earnings, yearly earnings, so that the shareholders, the Steinhoff scandal, so that the shareholders are under the impression that we are doing brilliantly well in the meantime, and that was not the case. That was the misuse of statistics that helped them to do that. Use alternative assessment methods to better understand and document student learning, folks, other than the ways in which it is currently assessed. Find better ways to do that. Better ways, because currently, if you look at the assessment, and I mean we said so in part 1, the assessment is really just testing, can the child find the mean? Can the child find the median? Does he know what the interquartile range represents? Instead of what the interquartile range represents in this data set. It's removed from the data set. It's just the middle 50% that's represented in the IQR. But does the child understand what the IQR tells us about the particular data? So finding better ways to assess them, other than mechanical, mathematical applications of formulas. You want to be more interpretive, you want more of a discussion, and you want more of an individual lens, a critical lens, on the data that you are using for that assessment. Okay, folks, I hope that gave us something to think about. Yeah. Please, if you learned something, like the video. Share it if you think somebody might appreciate the content in this video, and subscribe to my channel.